If we would look inside a skeletal muscle fiber, we will find out that the sarcolemma forms kind of transversal tubules that penetrate deeply into the sarcoplasm. Okay, so here are the openings into these transversal tubules. They come in a very close contact with parts of endoplasmic reticulum, which is called sarcoplasmic reticulum here, and it has got these dilated terminal portions. Inside the skeletal muscle fiber there will be, of course, the myofibrils inside, okay. So here we have the myofibrils, the sarcoplasma, the sarcolemma, these are the openings of the T-tubules, and this is a T-tubule in a longitudinal section. T means like transversal. Yes, these are invaginations of the sarcolemma. These are the terminal dilated parts or cisterns. Terminal dilated cisterns of smooth endoplasmic reticulum, and this smooth endoplasmic reticulum is called sarcoplasmic reticulum in this context of muscle tissue. Statistically, one T-tubule is linked with two adjacent terminal cisterns. So one T-tubule and two cisterns of sarcoplasmic reticulum form an associated structure called triad. This sarcoplasmic reticulum stores calcium ions inside. Why and how is this relevant to the contraction? Let's consider the sarcolemma and this invagination in more detail. This will be the transversal tubule. Here would be the terminal dilated parts of the sarcoplasmic reticulum. And in resting condition, they store most of the calcium cations. It has been actively pumped from the sarcoplasm. This is the sarcolemma. And here is the outside, and here is the inside of the cell. And we need to mention, at least briefly, some of the ion pumps that generate the electric inequilibrium on both sides of the sarcolemma. The most relevant here is an ion channel called sodium potassium ATPase, which pumps 3 sodium cations outside in exchange of 2 potassium inside. So we have more positively charged ions outside than inside. This generates a potential, a different potential inside and outside. You could even measure it with microelectrodes. If one microelectrode would be inside, another one would be outside, and you would put a sensitive voltmeter in between, you would be able to measure -70 millivolt in the resting condition, which is called the resting potential. Now, when it comes to action potential, there is a reversal of this charged particles concentration. So for a short period there is more positive inside and more negative outside, and this electric change is traveling along the sarcolemma, including the T-tubules. Then it activates other ion channels of the sarcoplasmic reticulum, and it opens channels that let the calcium escape into the sarcoplasm. So calcium is released into sarcoplasm, and this triggers the contraction. So you will discuss in more details many of these terms and objects and processes in physiology classes, but for now, for the first look, we understand how is action potential linked to the release of calcium. Now let's have a more close look on the steps of the contraction. Let us say we start in a condition where the double helix of F-actin is bound with the myosin head. So the myosin head is firmly attached to the actin. There's the F-actin, and the myosin head is attached to actin, which is a binding site for myosin. And next step, we need ATP that binds to myosin, causing its release from the actin. So there's a ATP, and once the ATP binds the myosin head is released. So it's not bound to actin anymore. In the next step, the hydrolysis of ATP occurs, which releases some energy. So ATP hydrolysis provides ATP plus the phosphate plus energy that is released. And this energy is used for a change of this angle. So the myosin head is cocked like a gun. Okay. The next step the phosphate is released and the myosin binds to the next binding site on the actin. Phosphate, the activated phosphate is released, and myosin binds the next available binding site on the actin filaments. And the fifth step uses the potential energy stored in this conformation of myosin and this potential energy is used for the power stroke, where the potential energy stored here is transformed to mechanical energy, and it's the force generating step. Of the whole process. And if you look more closely, the step number 5 looks exactly like the step number 1, but we have moved from this to this binding site. So there has been a sliding of the filaments. So this hole is called sliding filaments. If you look more closely on this, step 1 and 2, it's obvious that ATP is necessary for releasing the myosin head from the actin binding site. Therefore, without ATP, the myosin stays attached to the actin, and that's why after death, where you have no cell energetics, no new production of ATP, the ATP is gone, there is a condition called, in Latin, rigor mortis, and the muscles cannot move until lately the hydrolysis will occur.